Hello, organic chemistry students. We're getting ready to talk about organic reactions, and in particular we're going to start with reactions of alkenes. But before we start talking about specific reactions, I want to give you a little tutorial or a little primer on organic reactions in general. I want you to have sort of the bigger picture before we start looking at specific reactions. When we start talking about reactions, you're going to feel like we are just talking about reaction after reaction after reaction, lots and lots of reactions. In reality, we're only scratching the surface in this course, but it's going to feel like a lot of reactions to you. I hope that in this tutorial, this will help you sort of organize all of those reactions in your mind according to functional group. The vast majority of organic reactions can be divided into 4 different types. So we have the addition, elimination, substitution, and rearrangements. Here's an example of an addition reaction, and I want you to notice that we're starting with an alkene, and we're adding to that molecule HBr, hydrogen bromide. Whenever we have an addition reaction, you have to start with a site of unsaturation. You add something to that molecule to make it saturated. And you'll see that what we've done is added hydrogen bromide across the double bond. This is a typical reaction of alkenes, and we're going to talk about this reaction in a lot more detail a little bit later on. The second kind of reaction is an elimination, and in this example that I'm showing you, I'm starting with an alkyl halide, an alkyl bromide in particular, and I am eliminating from that molecule HBr and generating an alkene. In an elimination reaction, you start from something that is saturated, and you generate something that is unsaturated, and you lose some groups from that molecule. So in this case, we are eliminating HBr. Now you may have noticed that the elimination reaction is the exact reverse of the addition reaction. The next reaction is a substitution, and you'll see that what I'm starting with here is an alkyl bromide, and basically I'm replacing the bromine with some hypothetical atom or element or group that I'm calling Z. A substitution reaction, it's exactly what it sounds like. You're substituting one group for another group. Finally, we have the rearrangements. The rearrangements are very cool and very interesting. And you'll see in this particular reaction that I'm showing you, I'm not adding anything and I'm not losing anything. My starting material and my product both have the same atoms. All I've done is rearrange the bonds. So I've moved pairs of electrons to reorganize the bonds in that molecule. That's an example of a rearrangement. So we have addition, elimination, substitution, and rearrangement. I hope you can see that the names of these reactions really do describe exactly what happens. In this class, we're only going to cover addition, eliminations, and substitutions, so you don't have to worry about rearrangements. If the type of the reaction is what happens, the mechanism for the reaction is how it happens. A mechanism is the step-by-step process of bond breaking and bond making that happens during an organic reaction. We're going to talk a lot about reaction mechanisms as well. We can break reaction mechanisms down into 4 broad types. We have polar. So in a polar mechanism, we have bonds breaking heterolytically. What does heterolytically mean? Well, hetero means different. So when you break a bond in a polar reaction, you give the pair of electrons that makes up the bond between 2 atoms to one atom. One atom or group is going to be negatively charged, and the other atom or group is going to be short electrons. It will be positively charged. The vast majority of organic reactions fall into this category, and as a matter of fact, pretty much all of the organic reactions that we're going to be talking about fall into this category. Then you have the free radical mechanism. In a free radical mechanism, the bonds break homolytically. Well, what does that mean? Well, homo means same. What this means is that the bond that joins 2 atoms is broken, one electron is given to one atom, the other electron of the bond is given to the other atom. You generate a pair of what we call free radicals. Free radicals are any atom or species that has an unpaired electron. Free radicals are highly reactive. A small fraction of organic reactions fall into this group, and we'll see at least one example of this kind of reaction during this course. For synthetic purposes, most synthetic organic chemists, and those are people who make molecules for a living, don't really like these kinds of reactions. There are a few that are somewhat useful, but for the most part we don't like them because they're very hard to control. And finally, we have what we call the pericyclic mechanism. The pericyclic mechanism is really unique in that electron pairs are reorganized. It happens all in one single step. There are no polar or electron deficient species formed, no free radicals are formed. A pretty small fraction of organic reactions fall into this group, but most organic chemists really love these reactions because they're very predictable and they're easy to control, which makes them extremely useful for synthetic purposes. The rearrangement that I showed you on the previous slide was an example of a pericyclic reaction. You saw all three pairs of electrons moving at the same time. Now, before we really get into reaction mechanisms, I want to be sure that you understand the curved arrow notation that organic chemists use. A curved arrow is meant to represent the movement of electrons, and this particular curved arrow is meant to represent the movement of a pair of electrons. If at the end of the arrow, or at the head of the arrow, we have a double barb or two barbs, you'll probably understand that a little bit better on the next slide. That means we're moving a pair of electrons around. The tail of the arrow shows you where the electrons are coming from. So you're always going to start at regions that are electron rich, either lone pairs of electrons, ions, or pi bonds. The head shows where the electrons are going. You're always going to move electrons towards regions that are electron poor, towards cations or towards atoms that might have a partial positive charge. This particular arrow, now you can see that we have a single barb on the end of the arrow. That arrow is meant to represent the movement of a single electron, so that would be used in a free radical type of reaction. The tail shows where the electrons are coming from, and the head shows where the electrons are going to. Again, this type of arrow is used in free radical reactions. I also want to show you an energy profile for a reaction. An energy profile really represents the change in energy that happens as a molecule progresses from a reactant to a product. So on the y-axis we have the free energy, or the energy that's required, that's consumed during the reaction. On the x-axis we have the products of the reaction. We're starting on the left from reactants and ending up at products on the right. Delta G dagger represents the free energy of activation, or the energy that's required to overcome the activation barrier, the energy that you have to put into the reaction to get the reaction to go. At the top of this energy hill, we have what we call a transition state. A transition state is a species that exists at the top of an energy barrier. We cannot observe a transition state because it has a very short lifetime. We can only guess at what a transition state looks like. And we can make those guesses based on our understanding of the reaction mechanism or how a particular reaction behaves. This energy profile is for a reaction in which the products are at higher energy than the starting materials. So you have to put in energy to this reaction, but that doesn't always have to be the case. This energy profile represents a reaction in which the products are at lower energy than the starting materials. But we also see we have a smaller delta G of activation, and we also have a transition state. This particular energy profile represents a two-step reaction mechanism. In this energy profile, we have two transition states, and we also have a reaction intermediate. A reaction intermediate is a species that exists in a potential energy well. Even though it may be somewhat unstable, we can often observe them because they have a finite lifetime. So we have a pretty good idea of what a reaction intermediate looks like, as opposed to a transition state where we can only guess. So that was a very short primer on reaction mechanisms. We're going to move on and talk specifically about electrophilic addition to alkenes as our first reaction that we're going to cover in this class.